I'm going to talk about lenses now, and I want to be much more careful than I was in the previous video. Um, Lenses, there are two types of lenses. One is called convex and one is called concave. And convex, if we want to see what convex lens looks like, it looks like what we think of as a lens. That's a convex lens. Why is it doing that? There we go. A concave lens looks like a cave. Looks like that. Now we think of cave. You go in a cave. It's hollow. So convex or converging, concave and diverging. And we've seen with the convex lenses already that if you send light in towards a convex lens, parallel rays will converge at a focal point. And that's called the focal point. Whereas diverging is kind of what it sounds like. If you have a bunch of parallel rays coming here, they will spread out. And they spread out, I didn't do that last one very well, they spread out from a focal point on the other side. If I did these correctly, all of these would point back, whoops, at this focal point over there. So they appear to be spreading out. Now notice that the light coming in here, like this, doesn't actually reflect back. It goes out this way, but has this effect of looking like all those beams came from this spot right there. With all of these, there are two focal points. There's one over here. If you shine parallel light this way, it would come to a focus back here. And on this one, there'd be one in this direction. But we don't usually use both of them. For each situation, for each ray diagram that we're going to draw, we'll use one or the other. But it should be symmetric. I didn't draw it well again, but if this is 10 centimeters, that would be 10 centimeters. They're going to form images. Real is what we see when I held up a converging lens and it projected onto a screen. You can actually see it. Real projects on screen. Real projects on screen. You can hold up a screen and see it. Virtual, with a virtual image, it doesn't project onto a screen. It's not a real image. It's just something that appears there. If you think of a magnifying glass, you look through the magnifying glass, you can't project that onto any kind of screen. It's just what your eye perceives. So it's a virtual image. And then upright or inverted. With the previous situation, when we did a ray diagram, we saw that the image was upside down. So your eyeball forms a real inverted image. Upright, we're going to see a couple of cases where it's upright. A magnifying glass is like that. If you hold a magnifying glass over a bug, the bug doesn't look like it's switched directions. It's still upright. So let's really take a look now at how some ray diagrams go that are a little less obvious. So here's our principal axis. Here's our optical axis. The optical axis, remember, is the axis on which we put the lens. I am going to draw a converging or convex lens. And remember, we can draw it like this. We don't draw the whole lens necessarily. You can, but it's hard. It's really hard to do on this tablet. So it looks like this, where it comes to points at the end. And I'm going to pick an image. Now I'm going to pick an image that's really close. So here are my focal points. And I'm going to pick an object that's right there. Hope I did this okay. I pick an object that's right there. And remember the rules. One, first ray through the center is unrefracted. Okay, so I'm going to draw a ray from the top of that object straight through. It doesn't bend. The second one goes parallel till it hits the center of the lens and then goes down through the focal point. Okay, so first one was through the center, second one parallel, then through focal point. Okay, and it's a converging lens, so this parallel line would go down through there. You can see a problem. They don't come together. So when those don't come together, that means it's going to be a virtual image. It's not going to be an image that'll project on a screen. And to figure out where that virtual image is, we have to extend these lines back. And I like to use dotted lines for this because light doesn't actually travel here. I extend both of those angled lines back, and I'm going to have an image there. Let me do this. In this case, don't intersect. Extend backward. And then where those intersect, look at that. It's a coincidence that it ends up being near the focal point. The image will be virtual because these lines didn't intersect. It's these virtual light lines. And it'll be bigger than the object. So it's virtual, upright, bigger. And that's a magnifying glass. So I can't hold a screen up here on the other side of the magnifying glass and have it stick up. What's happening is, okay, if I've got a magnifying glass, there's a person over here with their eyeballs over there looking that way. And through the magnifying glass, they don't see the object, they see the image that appears bigger and appears a little bit farther away. I'll do some demo with this eventually. So that's a virtual upright bigger image. Now I'm going to do the same sort of thing, but for a diverging or concave lens. Principal axis, optical axis, and we draw this a little differently. We draw it like this, showing that it's wider at the ends and goes in, rather than drawing, trust me, you should be really happy I'm not drawing a really lousy concave lens. And the same sort of things, we've got a pair of focal points, and we've got an object. I'll put the object out here. And we want to find out what that image looks like. Going back really quickly to this one, notice, remember, we always put the head of the arrow right where the intersection is, and the tail of the arrow back on the principal axis. That's how we knew it was upright. So I come over here, and I've got to draw my rays. And there are two rays here also. Okay, the first one is going to be right through the center. That hasn't changed. And the second one, I should have had arrows on that, comes in parallel. But remember what a diverging lens does? Diverging lens goes away from that focal point. Okay, those should have arrows on them, but this is okay. Look, they don't intersect. We wouldn't expect them to, right? So we need to extend back only the angled ones. And that kind of indicates that I drew it pretty well because it goes back through the focal point. Now you can see where it intersects. And where it intersects here is right here. So I'm going to put the tail of the arrow there and, the tail of the arrow here and the tip of the arrow there. So what happens is you have a much smaller upright virtual image. Virtual, upright, smaller. Okay. Why would you use this? Well, you can think of this. I'm over here again, because since it's virtual, it's just what appears to somebody looking from the other side. So I'm over here, and I'm looking in that direction. Well, the object is way out here. It's far away. My eyesight's kind of lousy, so I need it to look closer. Notice this has moved so the image appears closer. And I feel like my dog's just about to start barking. Oh, okay. She ran away. So the image appears to be closer. That's great because my eye can focus closer. And I'm going to talk a little bit about how we view things, how our vision is in the next video. But this is the basic thing that you've got to remember. You've got to remember: 1, draw ray through center. Center. Straight line, right? Unrefracted. 2, parallel ray. Okay, comes to the lens and either goes through the focal point if it's a converging convex lens, or away if it's a diverging concave lens. If the 2 rays intersect, you draw the image. I'm going to put, if not, you extend backwards. If they don't intersect, extend angled lines only. Okay, and then finally you draw the image. And remember, drawing the image, you start from the principal axis and go to the intersection. And that allows you to determine if it's real or virtual. If you had to extend those lines backwards, it's virtual. If it's upright, if it appears the same way as the object, then it's upright. And you can make a judgment as to whether it's bigger or smaller.